Hi, this is Sabir again. Welcome to Computational Finite Difference Method. In this lecture, I'm going to make you understand what is the time-dependent problem. That means we have some equations, we have some problems in PDE, NOD that are related to time, and you have to calculate the time step or something like that to solve this problem. And there are two types of methods to solve this problem: explicit and implicit. So in this lecture, I'm going to focus only time-dependent problem and their methods, explicit and implicit, and I make you understand what is explicit and implicit method. Okay, begin. Let's begin with some equations that are related to time-dependent. For example, this. Uh, uh, for example, these are the time-dependent problem here. The first equation is the heat equation. Is the two-dimensional heat equation which is related to time-dependent. Temperature totally dependent on the temperature. Time. So we have to calculate the temperature in different times so that we can understand the variation of time, variation of temperature with time. So this is one of the education problems in geologically or in other engineering or other physical subjects. Okay, this is another time dependent problem which is called Schrodinger energy equation, which is also time dependent because our Schrodinger equation are dependent on time. Another equation we have here is the conservation of energy, which is also time dependent. This is from thermodynamics. Uh, the second law of thermodynamics from the entropies, inequalities of entropy, right? So this is also the time dependent. So in this lecture, I'm going to make you understand how we can solve this time dependent problem using the finite difference numerical method. And after this lecture, I'm going to implement some of these one-dimensional and two-dimensional problems in MATLAB and how to write code with that. Okay, let's get started with explicit and implicit. I have taken this definition from the arbitrary website, so I don't have any references here. I'm sorry. I do apologize for this. Okay, so what is the explicit? A finite difference scheme is said to be explicit when it can be computed forward in time using the quantities from previous time steps. For example, and I'm going to make you understand in the later slides, so you don't have to worry all about that. In implicit finite difference schemes, the output of time update depends on itself. So a casual recursive computation. Okay, let's skip this uh, slide code. Explicit. For example, here we have one-dimensional heat equation here, which is explicitly time dependent, right? Um, I'm sorry. Yeah, sorry, I didn't find this. Yeah. So this is the time dependent, right? And this is the temperature, TEM, and this is the one-dimensional spatial derivative. So this is the spatial in x-axis, right? So how we would solve this kind of temperature in explicit methods? So what are these explicit methods? In explicit finite difference becomes the temperature at time. In explicit finite difference schemes, the temperature this temperature, right? This temperature at time n+1 depends on explicitly on the temperature at time n. So temperature, so if we write down this, for example, temperature, say for example, this is the temperature at time n+1. That means the the next time step temperature. That means if we have temperature here at 0 degree, or if we have temperature say for example 0 degree, the next time step would also depend on the present time step. For example, the time step at point I is at point I is something like would be next time step would be for example the time at point I and something like that, and some other derivatives. So time step, the next time step temperature, the dependent on the present time step temperature, right? So in explicit finite difference schemes, the temperature at time step n+1, that means in future temperature depends explicitly on the temperature at time n, that means temperature the present at present temperature, then the future temperature depends on the present temperature, right? So this is the explicit method. The explicit finite difference discretion of the above equation. So if we discretize this equation, for example this, and in explicitly, then how we can write down? So we can discretize this following this T at future temperature minus the, we know right how to discretize this in finite difference at present time step discrete temperature time equal to k. So according to the explicit definition, we know uh, the present temperature, future temperature would be dependent on the present temperature. So all the other temperatures should be at present temperature. So the time step here is n, right? And this is minus 2. This is central difference. Central difference, so you know very well all about that. So this is the present temperature minus 2Ti plus Tni minus 1. So this is the del x square, right? So if we rearrange this equation, then we find this the future temperature here this is the future temperature, right? Future temperature at point I equal to time dependent, who's dependent on the temperature at point I at present temperature plus k delta t, say k delta t divided by del x square and t and I plus r at I plus I sum. You know the central difference discretization, right? So from this is the explicit finite difference, explicit finite difference came. So again, I'm going to make you understand that explicit finite difference is the method where temperature or velocity or everything, future temperature, future velocity or everything that you want to measure at future time should be dependent on the present time. Right, so you have to write down or you have to discretize our equation according to this definition. So we have discretized our equation according to the explicit definition. Okay, so we have some advantages. At the same time, we have some drawbacks of explicit method. For example, what are the advantages of explicit method? Uh, it is really very simple, as you see here, right? And as it is simple, so it should be a computationally fast. But we have another very bad drawback of this problem, and that is the stability of time. We cannot determine, say for example, here we have temperature at this room, say for example 25 degrees Celsius centigrade, right? But well, if you want to determine the what will be the temperature after 2 days, you cannot determine this from the explicit method, because the 2 days, the time, that means the 2 days should be determined in such a way that here we have formula k del t by divided square less than, oh sorry, this should be the half, less than or equal to um, less than equal to this or half, right? So from the time step we have to calculate the time step from this equation. So how we can do that? Let's how we can do that, let's calculate this. So we cannot determine the what the temperature in this room after 2 days, right? For 3 days, but we have to calculate what would be what would be the maximum time we can calculate from this equation. So these are the main drawback. Yep, definitely. If we want to calculate the temperature of this room on the basis of the present temperature, this could be erroneous or something like this. But anyone or somebody might be interested to find out the temperature. He or she couldn't do that with this explicit method. So how we can find out what is the maximum time step we can find out or calculate. So let's do that. So here we have the explicit k, oops, right? K, here the del t divided by del x square less than or equal to half, right? So we know it very well. So from here we can understand this is the k. I'm sorry, this is the k. So you can find out the del t. What is the maximum del t? For example, here this should be the del x square with a 2k. So this should be something like that. So del t should be determined in such a way that this del t should be maximum of this or less than this. So we cannot put the arbitrary time step here in explicit method. For example, here, right? So for example, um, at the present temperature at the room present. So for example, say, the present temperature at this room variation at different points, something like that. At time step t, at time step 0, right? So what would the next time step? So for example, this could be something like that. At time step 2, at time step 1, at time step 2. So even this might be a difference, another difference, something like that. Yeah. So this time step should be calculated from this explicit method or something like that. This so this is the only drawback of this explicit method. Otherwise, it is computationally really very fast and it is mathematically very simple as well. Okay, let's go to the implicit finite difference method. Implicit finite difference methods are nothing but simply opposite of explicit finite difference method, where the um, uh, in implicit finite difference schemes, the special derivatives, for example, del t square or x square, del square t or x square, are evaluated at new time step. That means the future time step. The simplest implicit discretization of the equation is, say, for example, of the previous equation, tn plus 1 minus I ti in at I point something like that, k into 1 half then x squared, or tn plus 1 at I plus 1, central difference, right? So in the explicit we have wrote only in the explicit we wrote this one is n, and all the temperature was n, right? But in implicit temperature, all the temperature should be at new time step, at the new time step. That means the future time step, right? So this is the implicit finite difference method. So if we rewrite this equation, then we could write down here some. So for example, here the temperature at point n plus 1 I uh, equal to uh, equal to k del t, right? K del t, k del t del x square times tn plus 1 I plus 1 minus 2 t I n plus 1 plus t n minus 1 n plus 1. And if we bring these terms out at this point, so we can write down t n for I, right? And of this should be closed by this whole thing. And if we write this, say for example s, right? For example s, we can write down this. Yeah. So if we bring out all the whole n plus 1 terms, n plus 1 terms, n plus 1 terms at the left hand side, and left we are left with only the n term, that means the present temperature, the right hand side, then we can find the following equation here. So we can write down the equation here. So for example, here t n plus 1 minus is, sorry, this is the I, right? At point I, we determine this at point I. Here at point I, at point I, this is the at point I plus 1, this is at point I, and this is I minus 1, right? So you can find out this S, right? S into t n plus 1 I plus 1 minus 2s t I n plus 1. Sorry, oops. Oh, so this should be plus, right? This should be plus here, and this should be, this term should be minus, and this term also be minus. Minus s t, sorry, oops, this should be the I minus 1 n plus 1, and this we are left only the I here, right? And here the from the right hand side, from the left hand side, you can take this um, 1 plus 2s t I n plus 1. So I at point I, this term and this term should be just the same way. Yeah, 1 plus 2s, so ti n plus 1, right? So then we are left only s t I plus 1 n plus 1, then we are left only minus s t n minus y, sorry, I minus 1 n plus 1. This should be ti at 1, something like that. So this is the equation, and we'll get the number of linear equation of something like that, something something like that at different points, right? So if we have more heat points, then we'll get the more. These are the only these are the equation for one heat point. So if we have several heat points, say example hundreds, then we'll get hundreds of equation like that, and then we have to solve this hundreds of equation in matrix form, right? So we must know all about the linear equations or linear algebra to solve this problem. So in this next lecture, I'm going to show you how we can solve this, or how we can uh, write code in MATLAB with this explicit and implicit, and we would find what are the advantages and disadvantages computationally we would find, right? We would see that. Okay, I hope you'd understand what is the explicit and implicit methods and what are the time dependent PD and ODE. And my main objective is of this course or of this lecture is to make you understand the how you can write down code in MATLAB with finite difference equations. Not my objectives are not to make you understand what is the PDA or the ODA, something like that. Okay, so I hope you enjoyed this course and I hope you enjoyed this lecture. Thank you very much, and I'm going to see you all again in the next lecture on how to write a code in MATLAB. Thank you.